Hello everyone, I'm Haike from Tsinghua University. Today I'm going to introduce our work Embeddings and Labeling Schemes for A-star. This is a joint work with Talya Eden from Boston University and MIT, and Piotr Indyk from MIT. A-star is a classical and popular algorithm for passbanding and has used in robotics and game solving since 1960s. Although A-star has good empirical performance, there are few studies on its running time analysis. A-star search uses a heuristic function to estimate the distance from one vertex to the destination. The quality of this heuristic function directly determines the performance of A-star. Traditionally, heuristics are chosen by experts based on the properties of the underlying problems. Recently, there is a trend to use machine learning to learn those heuristic functions. We try to understand the relationship between the heuristic function and A-star's running time. First, before starting our results, we want to formalize the procedure of A-star algorithm and some properties of A-star. Please see the pseudocode on this page. A-star starts with a set capital S, which only contains the source vertex S. At each time, A-star expands a vertex U with the minimum estimated distance, which is calculated by the distance from S to U du plus HUT, which is a heuristic function. Then the new vertex U is added to the set S and uses to update all the other vertices distance. This process ends when destination T is contained in S. Let's go through a toy example for A-star algorithm. This is a graph consisting of 6 vertices. We want to query the distance from vertex A to F. Black numbers are edge weights, and the blue label above vertices are the estimated distance lower bound from itself to destination F. In the beginning, in round 0, A-star starts with capital S equals A, the single vertex. In round 1, the first vertex to be expanded is B because the distance from A to B, 1 plus the estimated distance lower bound from B to S equals 2, which is the smallest among all the remaining vertices. In round 2, the next one to scan is vertex C. Then vertex E gets scanned, and finally vertex F is added to the set. If we do a comparison between A-star and Dijkstra, which always scan the vertex with the smallest distance to the start point first. Here, vertex D is not scanned even though it is near the source, because the heuristic estimates D to be far away from F. However, vertex B, not on the shortest path from A to F, is scanned too, because its estimated distance to the destination is too loose, wasting A-star 1 round to scan this wrong vertex. From this example, we can observe that the quality of the estimated distance lower bound decides the running time of A-star. In this page, we introduce 2 propositions for A-star: consistent heuristics and scan condition. Throughout our analysis, we only focus on those consistent heuristics, because according to Hart et al. 1968, consistent heuristics guarantee that the estimated distance crossing a fixed vertex U du plus HUT is monotonically increasing with time. Only under this situation, we are confident that stopping A-star when the destination is found won't miss any unknown shortest path. Therefore, consistent heuristics guarantee A-star algorithm's correctness, and we only consider A-star's efficiency when its correctness is guaranteed. The second one we consider here is its scan condition, also provided by Hart et al. 1968. Using consistent heuristics, one classic property here we say is that one vertex U will be scanned by A-star, in other words, will be added to set S before termination. If the distance from S to U plus HUT, the heuristic function, is smaller than the distance from S to T. If the equality strictly holds, then U must be scanned no matter other conditions. If this becomes an equality, then whether U will be scanned depends on the tie-breaking rule. If the inequality is false, then you won't be scanned by A star no matter which tiebreaker is used. The importance of tiebreaker will show up in the later parts of our slide, so we can ignore it for now. The metric for A star we consider here is called additive overhead on average, see definition 1.1. Before giving the statement of definition 1.1, we first give two notations. For graph G, capital P as T denotes the set of vertices on the shortest path between S to T, and SH as T is the set of scanned vertices for answering query S to T using heuristic H. And here is an example for these two notations. This is a picture in the last slide, and in this example, we query the distance from A to S, and PAS equals ACES, and SAS has an additional vertex B here, which is scanned by A star but not on the shortest path. And now we are able to describe our definition 1.1. We say heuristic H has additive overhead C on average if for a random chosen pair of vertices, A star scans C additional vertices than the minimum possible number of vertices. Note that our metric only takes into account the size of set S, but not the time spent by the whole algorithm. Here are some advantages for our metric. For example, this is a machine-independent quantity and doesn't depend on the data structure used to optimize the algorithm. Also, this metric only depends on the graph and heuristics. Before stating our results, we still need to give some restrictions on the type of heuristic functions we consider. The main heuristic functions we consider here are named norm heuristics and labeling heuristics. We think their generality can cover most of the commonly used heuristic functions. We first introduce our definition for norm heuristics, see definition 1.3. We first design a mapping pi, projecting each vertex to a point in a d-dimensional space, a half-dimensional vector, and then use the LP norm between two vertices as the estimated distance lower bound to be our heuristic function. Another heuristic we consider is labeling heuristics in definition 1.4. We first design an embedding F, projecting each vertex to a vector in a dimensional space with dimension L. Additionally, we allow the next function G to be arbitrarily chosen. In definition 1.4, we restrict one coordinate to take value from an entry from 0 to C. We have this restriction because otherwise even one coordinate can memorize infinite amount of information. The difference between norm-heuristic and labeling heuristic is that norm-heuristic has no requirement on the precision of each dimension, but requires that the function h to be a LP norm function, while labeling heuristic supports arbitrary function g, but requires that each dimension can only take value from 0 to capital C. We have another definition for heuristics. It's called beacon heuristic. Actually, beacon heuristic is a special case of L infinity norm heuristic, but we restrict our pi to take this specific function, which will be used later in the proof of our upper bound results. In this page is a table summarizing our main results. Our results provide lower bounds for norm heuristics and labeling heuristics, and also upper bounds for L infinity norm heuristic and labeling heuristics. In the remaining of my presentation, I will elaborate on this result table. We first look at theorem 1.6 here, which is the lower bound result for LP norm heuristic. Note that for theorem 1.6, the result also works for p equals infinity case, but because it is too loose, if the embedding dimension d, it is too loose if p equals infinity and can be covered by the next theorem, so we can ignore the second case for now. This theorem says that we can construct an n-vertex graph. If the embedding dimension d is smaller than n over log n, then A star will scan omega n vertices on average. Here LP norm heuristic covers the classical Manhattan norm and Euclidean norm. This is a quite strong lower bound because it says that A star's performance is almost no better than Z extra except a constant factor. The proof idea for this theorem is that under LP norm, for n vertex in a space with dimension smaller than n, it is impossible to form a equilateral set. Therefore, there must exist one distorted pair if the dimension is not high enough. See the graph below. We let C1, C2 to C4 be the equilateral set, but in the embedding space, they cannot be equilateral and there must be one distorted pair. We then amplify the penalty, which is the running time of A star, by constructing many auxiliary vertices connecting to them, this one and those one. Then we argue that A star when covering those pair of vertices, for example this one and this one, whose shortest path cross the distorted pair in the center, will suffer from very high running time. Next, we talk about theorem 1.7 on the lower bound for L-infinity norm heuristic. It says that we can construct a weighted n-vertex graph whose maximum shortest path consists of constant number of hops, such that if A star heuristic uses L-infinity norm in an embedding space of dimension d smaller than n to the power of alpha, A star will scan omega n to the power of 1 minus alpha vertices on average. Here alpha is an arbitrarily chosen parameter between 0 and 1. Additionally, our constructed instance in this theorem can be transformed into grids if alpha is smaller than 0.5, which is a result of theorem 3.4 here. Next page. Our proof idea for this theorem consists of 3 parts. The special property for L-infinity norm we use here is that L-infinity norm between two vectors depends on only one coordinate. If we call such coordinate crucial for this pair of vertices, then in the embedding space, each dimension can only contain a limited number of those crucial coordinates. Or some predictions will appear if there are too many crucial coordinates occupying the same dimension or orbit. Therefore, in this graph, we have a central clique A1 to AM. By carefully setting their parameter W, we can prove that at least one distorted vertex pair exists if the dimension is not high enough. Then we can construct some auxiliary vertices to amplify the penalties, like here those B's. Okay. Then we look at theorem 1.8, the lower bound result for labeling heuristics. Similarly, theorem 1.8 can also be transformed into a grid graph version for theorem 3.9 with an additional assumption, additional requirement that alpha is smaller than 0.5. Theorem 1.8 says that it says that we can construct a weighted n-vertex graph whose maximum shortest path consists of constant number of hops, and if A star used labeling heuristics with length L smaller than n to the power of alpha, A star will scan at least omega n to the power of 1 minus alpha vertices. Here alpha is an arbitrary parameter between 0 and 1. The result is similar to the last theorem. The graph constructed here is the same with the last theorem, this instance, but with different proof idea. The proof idea here is different from previous one because for labeling heuristics, we do not know any information about the function g rather than the norm heuristics. Therefore, the strategy we use here is that we reduce memorizing a set of random numbers to finding the shortest path, and then we apply the indexing communication complexity to prove our theorems. So now we turn our attention to upper bound results, theorem 1.10 and 1.12. Theorem 1.10 says that if A star can arbitrarily break ties, then beacon heuristics with beacon set n to the power of alpha enjoys average additive over hand n to the power of 1 minus alpha. The proof is very easy. A randomly selected beacon set can enjoy this result. The underlying analysis is that if we check A star scan condition, one vertex not lying on the shortest path will be scanned if the distance lower bound produced by it is better than all of those beacons estimation, which intuitively happen with probability inverse proportional to the size of beacon set. One thing I want to explain here is that our assumption on arbitrarily tie breaking. Recall A star scan condition DSU plus HUT is smaller than DST. If the equality becomes an equality, we said previously that this vertex U may or may not be scanned by A star. And this is the place where tiebreakers show up. Especially for beacon heuristics, ties are quite common, and how we deal with these ties can influence the final performance to a large extent. For theorem 1.10, we use an assumption to get rid of all the equalities and only take into account those vertices must be scanned. In our next theorem 1.12, it says that if we replace the arbitrarily tie-breaking assumption with a milder uniqueness shortest path assumption, we can construct a labeling heuristics automatically breaking all the ties and enjoy additive overheads n to the power of 1 minus alpha, still using embedding length L smaller than n to the power of alpha. Actually, our constructed labeling heuristic can guarantee that no tie exists in A star's vertex selecting process. The proof idea is that to break ties, we add an infinite small length to those not strictly tied estimated distance lower bounds. To do this, we only need to identify whether for a pair of vertices, the estimated distance is exactly the true distance. If all the shortest paths are unique, this task can be easily done by encoding the Euler tour of the shortest path tree rooted at each beacon and then check the location of two vertices on the shortest path tree. The encoding will only increase the embedding length by a constant factor. At last, let's return to the summary table. We have three lower bounds. Theorem 1.6 gives omega n lower bounds, which is relatively strong. Lower bound for L infinity norm here. And theorem 1.8, which is lower bound for labeling heuristics, they are similar. They both say that as long as the D or L, which is the complexity measure of the embedding, is smaller than O n to the power of alpha, then A star will suffer from omega n to the power of 1 minus alpha running time. We also give matching upper bounds in theorem 1.10 and 1.12. In conclusion, we theoretically studied the performance of A star algorithm by analyzing the relationship between the complexity of heuristic function and the number of vertices scanned. For non-heuristic and labeling heuristics covering the most commonly used type of heuristics, we provide matching lower bound and upper bound results. Our lower bound results are simple enough to be transformed into grid graphs with some additional parameter constraints, and thus useful for empirical studies. And that's all of my presentation. Thank you.